Not the official beginning of the talk yet. I'd like to introduce the speaker. Today's speaker is Dr. Vince Vatter, who got his PhD under the direction of Doron Zalberger back in 2006. It's a pleasure to have Vince here. Let me recommend today's issue just came out in my mailbox. American Mathematical Monthly had a beautiful article written by Vince Vatter. So now I have two students who have feature articles in the monthly, Andrew Baxter and Vince Vatter.
Didn't Laura and Eric also know?
Oh yeah, they have a note.
Oh,
So that, no, I couldn't, that doesn't count.
And this is Professor G, who I found out from Vince.
No, shush, you're full of nonsense, always.
Very, very hard.
Always full of nonsense.
Very hard broken. I have to find out when my day, Vince, if it's true, maybe you lie like you're gonna do.
Can I begin?
Yeah.
So I'm going to talk about grid classes of permutations. And the basic idea, I'm just going to review the prerequisites. There's a simple partial order on permutations. And grid classes attempt to study sort of sets that have some nice structure. And we'll try and prove some theorems about them. So basic idea is that every finite sequence without repetition, so sequence of numbers, is order isomorphic to a unique permutation. Okay, so for example, we had 2, 7, 1, 3, make that 5. That's order isomorphic to a unique permutation where the smallest entry is in the third position, the second biggest is in the first, then the third biggest is last, and the fourth biggest is second. Okay, so any subsequent, any sequence corresponds to a unique permutation. And our order, so this is our fundamental order here for the talk, is that sigma is contained in pi if pi has a subsequence order isomorphic to sigma. Okay, so essentially we just take the bigger permutation, you chop out a few entries, you find the permutation that's order isomorphic to that, and that's a permutation contained in the big permutation. Okay, and so just a couple more definitions here before we get started. A permutation class is a downset under this order. So if CE is a permutation class, and if pi is in C, and sigma is contained in pi, and sigma is in C. Okay, so the picture is that we're looking at all finite permutations, and we're taking a downset, which will look like this. And there will be some minimal things, like here and here, which aren't. They're minimal subject to not being in the permutation class, not being in the downset. And so we can give those a name. Okay, these we'll call the basis elements. Okay, so these are minimal permutations that are not Okay, so basis is sort of a terrible word for this. Usually we think of a basis as building the things. In this case, the basis is exactly the things that aren't built. They're exactly the things not in the class. And if you think about it, well, for any class, there is this set of minimal permutations that aren't in the class. And conversely, if I give you a set of minimal permutations that aren't in the class, you can build the class. So this is a unique description of permutation classes. So we can just write AVB to be the set of all permutations that don't contain anything in B. So beta is not contained in pi. For all beta in B. So if I take a basis, this would be the class that it determines as a AVB. So we just said that every class C can be expressed well in this way. So these are just the basic technical prerequisites, and now the questions that we might want to answer, or at least ask. Question 1 would be, let's enumerate this class. So enumerate C, and really we want to count the things with length n, so C intersect Sn. And this is traditionally where the enumerative combinatorics started in this field, as people took small bases, length 3, or 2 of length 3, or 2 of length 4, and they said, can I find the generating function for this? Okay. Question 2, we might want to, given a structural description of the class, find its basis. Okay. So instead of knowing the minimal things that are in the class, we know what everything in the class looks like. And we might want to ask about its basis. We might also just want to know, is it finite or infinite? So question 2 prime would just be there's a lot of other structural things we might ask about. Question 3, we could ask, does a class C contain an infinite antichain? Okay, so an antichain is a set of pairwise incomparable permutations. There are infinite antichains of permutations, but does our class contain one? If it doesn't, then it's partially well ordered, and we have a lot of nice things we can do nice tools that we can use on it. Okay, or we could, instead of the exact enumeration, which is quite hard in practice, we could ask just about asymptotic enumeration. So compute the limit of the nth root of how many things in the class there are. Okay. This is known as the growth rate of C. And just to give you an idea of how far away we are from solving all these problems. So this is the best known. So the growth rate of the class that just has a single basis element, 1, 3, 2, 4. It's at least 9.45, and it's at most 244. Okay, so this is the state of the art. These are the best known bounds right now. Okay, so those are some questions we might want to ask. So I want to get towards grid classes, which sort of, they're a way to take several classes and combine them in structure. So first, let me start out with juxtapositions. So let's say we have two classes D and E. The natural way to combine them would be to form this class C, which I'm going to express this way for this talk. Okay, it's two boxes, one box for D next to a box for E. This is all the permutations. Well, write it out here. Pi is in this juxtaposition if we can express pi, and this will what? We take pi and we slice it. The first part is order isomorphic to some permutation delta. The second part is order isomorphic to some permutation epsilon, where delta belongs to the class D and epsilon belongs to the class E. Okay, so that's a juxtaposition. For example, if we took AV21 juxtaposed with AV21, this is all the permutations that can be expressed as an increasing subsequence followed by another increasing subsequence. So we might actually draw these instead like that, two increasing subsequences, and you can compute that the basis here, it's the minimal things not in this class that can't be expressed in this manner, so you can see immediately 3, 2, 1 isn't in this class. Also, let's see, 2, 1, 4, 3, and that's the other one that's not in this class. 3, 2, 4, 1? No? Okay. I'll leave that as an exercise for the audience. There's one more basis element. It's minimally not in this class. This is a nice, simple class. We can actually do the enumeration right away. Okay, so the basis can be answered. The enumeration.
1, 4, 2.
3, 1, 4, 2. Yes, thank you. So there's our basis. The enumeration. Again, this is a theme we'll come back to later. What do we want to do? Well, one way would be to say that this is side A and this is side B. And as we read permutations in this class, we'll read them from bottom to top. And we'll write an A if the point we're reading is on the left, and a B if it's on the right. That's 2 to the n words. There's only one problem, and that's the problem that if we have a word that begins with A's and then switches to B's and never comes back to A, that's just an increase. Okay, and that's already counted by the all A word. So that's what we get. 2 to the n, all the words, minus the ones that all correspond to the increasing permutation. There's n plus 1 encodings of that. But you can see if you have a descent in your permutation, then you have a unique encoding. Okay, so that's our enumeration. Of course, that means that our growth rate is just 2. Okay. So let's see. We answered question 1. We started with a structural description. We found a basis. The basis was finite. This is all nice. There's no infinite anti-chain, and that basically comes from the words. So if you have a set of words, there's no infinite anti-chain in your set of words. And these are encoded by words, so it transfers. And then we computed the growth rate, which was easy because we had the exact enumeration. Okay, so in this case, we're done. So what can we do in general? Okay, so this is one of the first. This is one of the first really general results in this field. So Atkinson, in about 1990, I guess I'll say 7. Somewhere around there, he proved this result. And this is really, like I said, one of the first results where people started to think about proving things in general. So general constructions. So the basis for this juxtaposition, DE consists precisely of permutations of the form. Let's say delta, gamma, epsilon. So I'm viewing these just as concatenations of subsequences, where there are two ways this can happen. The first way is that you could have, the middle part could have size 1, and then the rule is that the first two, the delta gamma part has to be a basis element for D, and then the gamma epsilon part has to be a basis element for E. So delta gamma is in the basis for D, and then gamma epsilon is in the basis for E. And the second case is just that the middle entry is empty, and then, well, delta is in the basis for D, and epsilon is in the basis for D. Okay, so this is a very nice theorem because it tells us, given two classes that we know a lot about, it tells us everything about their juxtaposition, in terms of at least the basis. So the basis, if the two classes D and E have finite bases, then of course this class has a finite basis. And also we can implement this in a computer. So I have a computer program where you just input the two bases, and it outputs the basis for the juxtaposition. So that aspect is essentially completely done. What about the enumeration? Well, okay, let's try the exact enumeration problem. The problem you get into here, though, is that a lot of different permutations can have a lot of different representations in terms of a juxtaposition. So here, we don't have any success. There's no general solution. And I guess it's not really a solution we'd want. It's more of an algorithm. Okay, so we'd like, if we knew about the enumeration of the classes D and E, we'd like to put it into a maple package and get out the enumeration of their juxtaposition. Okay, but we don't know how to do that, so that's a challenge for maple. But what if we were...
But there may not be internal algorithm.
There might not be.
Yeah, probably not.
But what if we...
Many special cases are algorithms.
Yes, and in special cases there are algorithms. Although not that many special cases.
Yeah.
So what if we just worry instead about asymptotic enumeration?
You mean an efficient algorithm, by the way. Algorithm exists.
Oh yeah, just count them. Yeah. Okay, so what if instead we lower our goal to asymptotic enumeration? Well, here there is a nice answer. So if we take the number of permutations in this juxtaposition of length n, well, how do you form something from this juxtaposition? You essentially choose where is this divider going to go. And let's say that it goes k in, and then there's n minus k here. So you choose where the divider is going to go. You choose something from d of the right length, something from e of the right length, and then you choose the values for the thing in d. So this is, the number of length n is very close to the sum from k equals 0 to n of, well, we choose our values. All right, we choose our values that the thing from d is going to get. Then we choose which thing in D we put in there, and then which thing in E we put in there. Okay. And that's that. Well, if D and E have growth rates, and I should have mentioned when I find that limit that we don't know if it exists in general, but if these two have growth rates, then this is approximately, well, n choose k, the growth rate of D to the k, times the growth rate of E to the n minus k. And of course, that's exactly the binomial theorem. So the growth rates add. So this is the growth rate of D plus the growth rate of E to the n. Okay, so we weren't able to do the exact enumeration, but we were able to get a nice answer for the asymptotic enumeration. Okay, so that's the story with juxtapositions, which is all fairly well known. Now let me move on to what I promised to talk about, which is grid classes. Okay. Juxtaposition just says put things next to each other. Of course, we could put them one on top of each other. But what if we wanted to do this? We wanted this hook shape. We want all permutations that can be divided into that in that manner. So I mean that pi is in this hook if, well, pi equals delta epsilon, I guess gamma. These are all sort of order isomorphisms because these are actually subsequences. Where they belong to the respective classes. So in juxtapositions, we knew everything. Here, we write down the questions. The basis, unknown in general. We don't know even if it's finite. Enumeration, of course, since we can't do juxtapositions, we can't do this, but how about growth rates? That's also unknown. Okay, so we're just taking this tiny step of allowing things to be in a grid instead of in a row, and we've lost all of our theorems. And to give you a hint of why this growth rate thing might be sort of difficult, if I did the growth rate of, I'm going to make these all increasing segments, so that means that they avoid 2, 1. Okay, it's not 3 or anything, it's 1 plus the square root of 2. Okay, so more interesting numbers are starting to come up. Okay, this is also almost the only one I know, so that's why it was easy to choose as an example. Okay, so this is clearly we've generalized too much, so now let's come back. Let's look at monotone grid classes. So the rule here is that every cell is increasing, which means it consists of the class of things that avoid 2, 1. Decreasing, where they're allowed to be empty. Okay, these are the cells that I don't even bother to write up here. Okay, well this is a restricted class. Maybe we can prove some things. Let's look at an example. I'm going to make this a decreasing segment, this an increasing, this an increasing, so the picture you should think of, although in a few minutes I'm going to tell you why this isn't a good picture, but the picture you should think of is that. Right, so it's decreasing, increasing, increasing, decreasing. So it's like an X, so at least morally it's like an X. Okay. This was the first example of these that was studied, and it was studied by accident under the name of skew-merged permutations. If you think about it for a little bit, these are precisely the permutations which can be expressed as the union of an increasing subsequence and a decreasing subsequence. So the union of an increasing and decreasing subsequence. In that way, I mean, the initial interest of this was that if you avoid 3, 2, 1, then you're the union of 2 increasing subsequences. So what if I change one of the increasing ones to a decreasing one? Well, in this case, and these are 2 classic papers now, the basis is 2, 1, 4, 3, and 3, 4, 1, 2. And it's Stankova. In the 90s. Okay, so just 2 permutations describe this class. And the enumeration is 1 minus, so I'm going to give you the generating function. It's 1 minus 3x over 1 minus 2x times the square root of 1 minus 4x. And this is Atkinson. Also in the 90s. Okay, so it's a very ad hoc argument that doesn't generalize beyond this case. It's very specific to this case of scheme.
Does it have a scheme?
You know, I don't think it does. But you should check it. So yeah, I don't know a systematic way to get this generating function. Okay, but notice that it's algebraic.
So use the fact that it's like an X, everything?
Mm-hmm. Yeah, he colors all the entries in certain ways. Okay, so what about general questions? So our first general question would be, do monotone grid classes have finite bases? And you would think, maybe, I mean, this is what I think, that, you know, at worst, to describe a basis element of this, you'd need like 2 entries per cell to kind of peg that cell in the correct order, and then 1 bad entry that's where it's not supposed to be. So you'd think you'd need at most, 2 times the number of cells plus 1, but we've never been able to prove that. So this is still unknown, and it's a very frustrating problem to me at least. Because it seems like you should be able to prove this pretty easily. And then, another thing we want...
Are there other non-examples besides this one?
There are a couple more, but that's it. Okay, and the other question, generalizing from this, and this is the only one that's not really a juxtaposition class, and not what I'm going to talk about later, where we know the generating function. But are they always this form? So are they always algebraic? And that's also nope. So again, we've asked the general questions and we haven't been able to answer them. I will give you the one general result we know. So this is to Maximilian Murphy and myself. We were looking at these monotone grid classes, and we were interested in the infinite antichain question. Can we make an infinite antichain of permutations in these things? So